Earth Systems 3209, Unit 4, The Forces Within Earth. Unit 4 references can be found in Chapters 4, Chapter 15, Chapter 16, and Chapters 19 in the textbook, and also in Appendix A and Appendix B of curriculum guides. Unit 4, Topic 2.7. This topic will look at plate boundaries, and in particular, transform plate boundary. We'll focus on describing a transform boundary, and also focus on drawing a transform boundary which demonstrates the relative motion associated with the boundary. When we look at plate boundaries, according to the plate tectonic theory, three different boundaries exist at the edges of tectonic plates. One being a divergent boundary, which is also called a ridge. Number two being a convergent boundary, which is also referred to as a trench or subduction zone. And number three is a transform boundary. Information on these different types of plate boundaries can be seen in your text on pages 526 to 539, and also you can look at figure 1917 on page 528 to see the location of these boundaries in relation to the world. When we look at plate boundaries, a transform plate boundary is characterized by two plates grinding past one another without the construction or destruction of crust. So at transform plate boundaries, we do not see any crust being created, nor do we see any crust being destroyed. The movement along a transform boundary is caused by convection currents, which exert shear forces on opposing plates, forcing them to slide past one another. And the lithosphere is neither created nor destroyed at these transform plate boundaries. So if we look at the diagram above, we see that plates are actually moving apart from one another, and this would be located on the ocean floor along a ridge. Here we see two plates moving past one another along a ridge. Over here on this side we see two plates moving away from one another along a ridge. But in between, where the ridge is separated, we see opposing plate motion, and this is defined as your transform fault boundary. The plate located above the transform fault boundary is moving to the right, whereas the plate located below the transform fault is moving to the left. And this opposing motion is called a transform fault. And these are found on the ocean floor, where we see the mid-oceanic ridge offset as it winds its way down the middle of the oceans. Transform plate boundaries are characterized by this type of boundary was discovered by J. Tuzel Wilson. Wilson proposed the existence of transform faults to explain the numerous narrow fracture zones and earthquakes found in the Earth's crust. Wilson realized that ridges at divergent plate boundaries were not perfectly linear, and came to understand that transform faults exist where segments of the ridge are offset, and this can be seen in the diagram below. The dark areas, dark lines, represent the mid-oceanic ridge, and where the mid-oceanic ridge is offset, we find what's called a transform boundary. And along those transform fault boundaries, we see the two plates sliding in opposite directions, therefore created by shearing forces. And these shearing forces will form what's called a transform fault. Most transform faults occur where oceanic ridges are offset on the ocean floor. And again, this can be seen in the diagram to the right. Also, along transform fault boundaries, earthquakes along such transform faults are occurring as shallow focus earthquakes. One of the largest such transform boundaries occurs along the boundary of the North American plate and the Pacific plate, and this boundary is known as the San Andreas Fault. Here, the transform fault cuts through the continental lithosphere, and we can see a representation of the San Andreas Fault in the diagram to the right. We see relative motion of the Pacific plate moving upward and to the left, whereas the North American plate moves down and to the right. Along the red line, we see the two plates that are sliding past one another, and it intersects with the continent. This fracture line is called the San Andreas Fault and is the site of many earthquakes throughout history. When we look at transform fault boundaries, we can look at the diagrams below. There are two examples of transform fault boundaries. One is called a right lateral transform fault boundary, and the other is called a left lateral. To determine a right lateral transform fault boundary from a right lateral transform fault, we need to look along the fault line. So the fault line in this case would be the line that connects the two opposing plates. So if we were to stand in this position and look upward along the fault line, we determine which type of transform fault we have by looking at which plate is moving toward you. So in this situation here, when we look up along the fault line in this direction, the left plate moves towards you. So this transform fault is referred to as a left lateral. A left lateral transform fault. Again, if we move over to the diagram to the right, and again we look along the fault line. In this case, we notice that the right side of the fault line moves towards you. So this one is referred to as a right lateral transform fault. So to distinguish between the two different types of transform faults, you would have to stand along the fault line and look in the direction of the fault line. Whichever plate moves towards you, that would be the type of transform fault you're looking for. So in the first diagram, diagram A here on the left, that would be called the left lateral transform fault because the left side moves towards you. And on the right, diagram B would be called a right lateral transform fault because the right side of the fault moves towards you. Even if you went to the other side of the fault and looked in the opposite direction, this is your eye looking in this direction, same idea. You'd be positioned opposite to where you were on the bottom, and the right side of the fault line would be moving towards you. So again, it would be a right lateral transform fault. So if we look at the different types of plate boundaries, we have three different types of plate boundaries located on the edges of tectonic plates. These being divergent, convergent, and transform. If we look at the divergent boundaries show spreading caused by tensional forces where two tectonic plates move away from one another. These are known as constructive boundaries because oceanic lithosphere is being created. We generally see a ridge or a rift at these boundaries, and we do see volcanic activity at this boundary. It should also be noted that there is no earthquake activity found along divergent plate boundaries. In the diagram down below, we see the relative tensional forces moving away from one another, causing the two plates to move in opposite directions, which creates new ocean floor by the rising magma that comes up and crystallizes at the surface. So this would be an example of a divergent boundary. At a convergent boundary, we generally see the motion where two tectonic plates move toward one another by compressional forces, and one tectonic plate subducts beneath the other, which generally forms a subduction zone. These boundaries are called destructive boundaries because oceanic lithosphere is destroyed as the subducting plate melts in the mantle. And they're found, or one feature that's generally found associated with convergent boundaries would be a trench. Along convergent boundaries, we do see volcanic activity, and we also see earthquake activity. In the diagram below, you'll notice that earthquakes, they're located near the top of the subduction zone, are called shallow focus earthquakes. In the upper portion of the mantle, they're called moderate earthquakes. And in the deeper mantle, they are called deep ocean or deep focus earthquakes. And the third boundary, which was the focus of this lesson, would be the transform boundary. Transform boundaries show lateral sliding, where two plates slide past one another. They are conservative boundaries because no lithosphere is being created or destroyed at these boundaries. We generally don't see any major feature on the surface, just the transform fault itself, and we don't find any volcanic activity associated with transform faults. But we do see earthquake activity, and this earthquake activity is located near the surface of the Earth, and therefore are referred to as shallow focus earthquakes. Let's look at some examples. Examples taken from past public exams. The first question reads, what boundary is not associated with volcanic activity? So if we look at the four choices, convergent boundaries, divergent boundaries, and rift zones, all three of these have volcanic activity associated with them. Whereas a transform boundary, where we see two plates sliding past one another, no lithosphere is being created or destroyed, and we don't see any volcanic activity. So our answer to the first question will be D. A transform boundary do not have volcanic activity associated with it. The second question reads, which plate boundary does shear forces dominate, resulting in tectonic plates sliding past one another? So when we look at shear forces and two plates sliding side by side in opposing directions, this is characteristic of a transform fault boundary. So the answer to the second question will be transform boundary, which shows shear forces dominating, causing two plates to slide side by side. Example number 2. First question reads, which main type of force results in a transform fault? When we look at transform faults, we generally see two plates sliding side by side in opposing motions, and this is caused by shearing forces in the mantle, where your convection currents move in opposing directions, causing the plates to slide past one another. So the answer to this question would be the forces associated with transform faults are shear forces. B. Second question reads, which of the following is an example of a transform fault boundary? When we look at our choices below, we see the Alaskan thrust fault, we see a Japan trench. Both of these are associated with subduction zones. Then we see the San Andreas Fault and a Tokyo normal fault. Whereas a normal fault is associated with compression forces, tension forces, and we see vertical motion of two tectonic plates. But along the San Andreas Fault, this is a fault located in California where two opposing plates slide side by side. The Pacific plate and the North American plate, they grind past one another, which forms a transform fault boundary. So the answer to this question will be C. The San Andreas Fault is a transform fault boundary located in California, in North America. Your turn. Take the time to complete the following questions. You can pause your recording now to prepare your answer, and the solution will follow. Question reads, which occurs at a transform plate boundary? Our choices are collision of plates, formation of crust, sliding of plates along each other, and subduction. When we look at the answer to this question will be C, the sliding of plates along each other. Along a transform fault boundary, we have shearing forces which cause two plates to move in opposing directions, therefore resulting in the slotting of the plates along each other. So the answer would be a transform plate boundary would demonstrate the slotting of plates along each other. So the answer is C. In summary, when we look at a transform fault boundary, transform fault boundaries were proposed by Wilson. Transform fault boundaries demonstrate shear forces which causes plates to move past one another in opposing directions, which result in what's called the transform fault. We can have two different examples of transform faults. We can see right lateral transform faults and left lateral transform faults. The secret to determining which type of transform boundary you see is to look along the actual fault line, and whichever side of the tectonic plate moves towards you, that's the actual type of transform fault that you would have. So a right lateral transform fault would have the right side of the transform fault moving toward you. Most transform faults will occur along ocean ridges on the ocean floor, and these are responsible for offsetting the ocean ridge, enabling it to wind its way down through the middle of the oceans in between the neighboring continents. Transform fault boundaries also have no volcanic activity. They just have shallow focus earthquakes associated with them. Along the transform fault boundary, the lithosphere is neither created nor destroyed. And examples of the transform fault boundary will be the San Andreas Fault, which runs through California in North America. So these are the main points of transform fault boundaries.